Lesson 2 of electrochemistry. I thought of bringing a change of clothes, but you know, whatever. You guys are off on your snow day, and half of you probably won't even watch this. No, only kidding. I noticed that I missed a couple things from the first lecture, and that was reactions that are not redox. So classic reaction that is not a redox is a double replacement. And let's look at that. Lead 2 acetate and sodium chloride, and we'll just balance it here. Sorry, so used to making that iodide. All right, so this is double replacement. And this is not redox because the charge never changed, did it? Lead started at 2+, ended at 2+. The acetate started at 1- and ended at 1-. And the sodium +1, the sodium +1, the chloride -1, the chloride -1. So remember, we first got to identify a substance as either redox or not, and this would definitely not be one. Okay, another thing was I had the last problem, lesson 1 on page 2, was a you try it. If you were in class, I'd have you go to the whiteboards for that. For those of you who actually did, you should have had a final balanced equation of 2Fe3+ plus Sn2+ goes to Sn4+ plus 2Fe2+. And we'll notice that the tin was oxidized and the iron was reduced. I like this one because you can go from one oxidation state to another. It doesn't always have to be 0 to plus or 0 to -2. So this just allows you to see that, especially when you have transition metals with all those multiple oxidation states, or your heavier group, main group metals that have those 2 oxidation states. So that's a couple of things from lesson 1 that I overlooked, and I apologize for that. But let's go on to lesson 2, because it's kind of a fun lesson. It's one of those things that's technique more than you know, big concept or abstract thinking, and it looks cool because you can fill up the board with one problem. And that is balancing redox reactions in either an acidic or basic solution. Now, the purpose of this is sometimes just getting ions in water, they won't really react. They just sit there. But if we change the pH of the environment by adding a little bit of acid or a little bit of base, it's not anything we really even measure out. It'll just say a few drops. If we change the environment by making acidic or basic, then we can actually get those ions to react and be reduced or oxidized. So we can force a transfer of electrons by changing the environment to an acid or base. However, what happens when we do this is that we draw water in, okay? When we usually have 2 ions in an aqueous solution, water is just pretty passive. It just sits back and watches. However, if it's an acid or a base, well, water gets in on that, doesn't it? We know from Arrhenius that it says it increases the hydrogen ion concentration, it increases the OH. Well, in doing that, we draw in water and ionize it. And so we have to factor in how water is in that equation. And so we balance these a little differently. And let's just jump right in and see one. When potassium permanganate is reduced by sodium oxalate in an acidic solution, it produces the manganese 2+ ion and carbon dioxide. We wouldn't expect you to predict the products of these. Now, they used to back in the day. You had to know, but no more. All right? Thank goodness for the dumbing down of the test, right? So now they're just going to give you the reactants and the products in this. They just want you to balance it. So we start out with this. We have this permanganate ion and oxalate. And in an acidified solution, it will actually force the transfer of electrons. Okay? And our job is then to balance this and take into account how the acid reacts with the water. All right, so here's the process. We're first going to look at what the half reactions are. What happened to the manganese going from reactant to product, and what happened to the carbon going from reactant to product. So we start by saying, okay, here's MnO4, and it goes to Mn2+. Okay, so that's one of our half reactions. The other half reaction is I have this oxalate, and it's going to carbon dioxide. And as you can see, in and of itself, you're not going to balance these, are you? Because you know, we've destroyed matter here. We have oxygen as a reactant, and it's nowhere to show up. Okay, so there's a special way of balancing this in an acidic solution. And once again, I've written the steps that you take in your lecture notes in that little box. And the first step is always to start with your half reactions. Okay, that's going to be the skeleton that you're going to put some muscle and flesh on in just a minute. So let's start with just this one. Okay, let's work through it. All right, so MnO4 going to Mn2+. All right. Now it says the first thing that I'm going to do is balance the other ions, meaning anything other than oxygen and hydrogen. All right, so I have one manganese, I have one manganese, so I'm good. All right, so that's done. Step 3 is balance oxygen with water. All right, so I have 4 oxygens on this side. So to balance those 4 oxygens, I need 4 waters. All right, now it almost seems like it made it worse, didn't it? Now you've added hydrogens. Well, we can fix that. Look at step 4. Balance hydrogen with the hydrogen ion, because that's where the acid came in, right? So I've got 8 hydrogens, so over here I'm going to put 8 hydrogens. Okay? This takes into account then, this is an acidified solution, and this is how it reacted with that water. That brings that in. Okay, we're not quite done here, because we have now balanced mass, but we have not balanced charge. All right, so let's look. On this side, we have a total of +7, don't we? On this side, we have +2. Okay, so if I add, let me scoot my arrow over a little bit. If I add 5 electrons to this side, then I've balanced both mass and charge. Okay, so this half reaction is good. Now we're going to do the exact same thing with this half reaction. All right? So I'm going to write this one just, I should write it right under it. So let's start. I've got the oxalate ion going to carbon dioxide. Now the first thing that my steps say, I've got to balance the other ions. So I've got 2 carbons on this side. I need 2 carbons on that side. All right. Now that I've balanced the carbons, I balance oxygens with water. Well, I've got 4 oxygens on this side, and I've got 4 oxygens on that side. Wow. Okay, that one came out pretty easy. So we're done balancing this half reaction. We didn't have to use water and hydrogen to do it, and sometimes it works out that way. Okay, we've got the mass balance, but now we need to get that charge. I've got a -2 on this side, so I have 2 electrons on this side to get that charge balance. So we see that in this equation, once again, it even said it in the problem, the manganese is reduced, isn't it? And the carbon is oxidized. All right, but now the idea is to write the balanced chemical equation for this. We're balancing this reaction in an acidic solution. So before I can add these together, I've got to have the correct number of electrons. Okay? I've got 5 going in and I got 2 going out. I have to have the same number. All right? This one will be fun because what is the lowest common multiple of 5 and 2? Well, it's 10. So that means I need to take everything in this top reaction times 2. I need to take everything in this bottom reaction times 5, don't I? All right, so let's look at that. When we do that, and we add these together, we'll get 2 manganese, permanganate, 16 hydrogen ions, and 5 oxalate ions. And on this side, we're going to have 2 manganese 2+ ions. We're going to have 8 waters. And we're going to have 10 carbon dioxides. All right? So that's writing the balanced chemical equation of the permanganate ion being reduced by oxalate. Okay? In an acidic solution. What else do I want to say about this? All right. We usually do this by a titration, and this is really cool because, and we probably will do this one in lab, I hope. There's a few labs I want to do with electro, and we'll see how time goes. But permanganate is purple, all right? Oxalate is colorless. But as you convert this purple permanganate, this goes to a different color. Can't think of what it is right now. And so you don't need an indicator. It's self-indicating because you'll see when that purple goes away is when it has reached its equivalence point, so to speak. So these are called redox titrations, and in redox titrations you're looking for the color change that goes from these transition metals changing oxidation states. All right, so this is an example of balancing an equation. All right, if we were in class, I would now say get out your whiteboards and try these next 2. So what I want you to do is turn off the video, try these next 2, and we'll come back and work them out and compare it to how you did. All right, now turn it off. We're back. Amazing that. I really need a pause button on this video, but the limitations of an iPad, huh? All right, so let's try these 2 to see how you did. And I'll go through them quickly because we should be just checking. We've got dichromate going to the chromium 3+. All right, and let's work through and do this one first. This one says we've got to, balance the other ions, so I need 2 chromiums to balance that. I've got to balance my oxygens with water, so 7H2O. And then I balance the hydrogens with the hydrogen ion, because this is in an acidic solution. And then I look and I have a +6 on this side and I have a +12 on this side. So it's going to take 6 electrons to balance that. On the next one, I've got the chloride ion going to chlorine. Right? I need to balance this. There's no oxygen to worry about, so now I just need to balance the charge. And this requires 2 electrons. Okay, before I can add those together, I have to have the same number of electrons going in as I have going out. So I'm going to multiply this one times 3. And what I have is 14 hydrogens plus 1 dichromate. Oops, that's minus, sorry. plus 6 chlorides going to 3 chlorines plus 2 chromium 3 plus 7 H2O. Okay, now you always want to check your final answer because these can get dicey, especially if you've got water and hydrogens in both half reactions and you have to simplify them. We haven't had any yet like that. But what I do to check is I just say, is my charge right? If your charge is right, you've probably done it right, okay? So let's look. We've got 14 plus, minus 2 minus, and 6 minus is minus 8 minus, so I've got a 6 plus on this side. What do I have on this side? 2 times 3 is a 6 plus. So since my charge is the same, I'm pretty confident that I've done this correctly. All right, let's try the other one. All right, we've got the other one. We've got copper going to copper 2 plus. This is another one because we have no oxygen or anything. This is an acidic solution, but we're still just going to balance it then by mass and charge, and that half reaction's done. That one's easy. And then we have the other one, the nitrate ion is going to nitrogen dioxide. The nitrogens are balanced. I move to my next step where I balance oxygens with water. And then I balance my hydrogens with the hydrogen ion. And then I've got a plus 2 and a minus 1 is a plus 1. This side is 0, so I need to throw in an electron. Sorry. So I should have just one electron here, shouldn't I? Looks like I've done something wrong in my, yeah. Okay. Obviously, the copper is oxidized and the nitrogen is reduced. All right. Before we can add these together, we do have a discrepancy in the number of electrons. So we have to fix that, and we fix that by multiplying this whole thing times 2. Okay, so we have 4 hydrogens plus 2 nitrates plus 1 copper goes to 1 copper 2 plus 2 nitrogen dioxide plus 2 H2Os. Doesn't matter which order you put these in, absolutely not. But just to check and make sure we did this right, we got a plus 4 and a minus 2, so we have a plus 2 overall. On this side we have a plus 2 overall, so chances are we've done this correctly. All right. Now, an interesting twist to this. It's really important that you know how to do this and you know how to do it quickly. For this reason, on your multiple choice, what they do occasionally on the exam is they'll throw in something, either an acidic or basic, they won't tell you which, and they'll just say, as in the bottom of page 3 in your lecture notes, on the exam it'll say, what is the coefficient when this is balanced? All right, so let's look at, you've got, they want to know when this equation is balanced, what would be the coefficient in front of that H? Okay, well the first thing you got to say, well, is this in an acidic solution or a basic solution? All right, obviously it's acidic, else we wouldn't have H. If we're a basic solution, we would have this, wouldn't we? Okay, so first of all, this is an acidic solution. So what I'm going to do to figure out what the coefficient is is cheat, because if you look at that, you go, oh my word, I can't get this. Yes, you can. You're going to ignore the H and the H2O on the product side and just do the half reactions and balance it. So let's look at how that looks. Oh boy, that's great grammar. That's 1 half reaction. Okay, I've balanced mass and charge, and I get 1 electron, correct? All right, the other half reaction is MnO4 going to Mn2+. All right, my manganese balance, I'm going to add 4 waters to balance, and then I'm going to put in 8 hydrogens, all right? Now, before I just plug that number, I got to make sure and check if I have to do any additional multiplication, don't I? So let's look at this. I've got a +8 and a minus and a +2, so this is going to require 5 electrons. Before I add them together, I have 5 going in and 1 going out. So the only thing that's going to change on coefficients is the iron, correct? So these will stay the same, so 8 is the number. See, I didn't even have to put those together. And so the answer to that question then would be 8. How did I figure it out? I first of all realized this is an acidic solution. I ignored the hydrogen and water for now because that's the end result, isn't it? And went back to what would be the original half reactions and then figured that. And that's one of those on the exam where I say the first thing you're going to do on those 60 multiple choice is cherry pick, is just go through and read every single one, and those that you can answer in 30 seconds, answer them now, leave the other ones blank where you have more time. And this should be one of those that you can get in 30 seconds, all right? Because you don't have to do that much. You know, had this been a 3 electron and 2 electron, then we would have known we had to multiply all this by 2, and that would have changed it to 16, and we're done. So you need to be able to do these, but do them quickly, because if you do these quickly, not only can you get an answer correct on the multiple choice, but you can get an answer correct quickly, and that'll save you more time for those others that require a little bit of thought. All right, so that is the procedure that we go through for balancing an acidic solution. What if it's a basic solution? What if this reaction won't do anything in acidic, but we change the environment and make it more basic, raise the pH? Okay, well, it's very, very similar. In fact, we're going to start it the exact same way that we start an acidic solution. So let's look. They tell you balance it in a basic solution. They'll let you know, or they'll say a pH of 9. Okay, hopefully you'll know that's basic. Or if on like that, which would have a coefficient? Look, is there an H or an OH in the equation? Then you'll know. Okay, so here's our equation. The cyanide plus permanganate and cyanate ion. Notice in a basic solution that our permanganate goes to something different. And yes, you used to have to know that. You don't anymore. Hallelujah for the dumbing down of the test, right? Okay. So, let's just pull out one half reaction at a time. Cyanide going to cyanate. All right. Our carbon and nitrogen are balanced. We start with that. And then we balance oxygens with water. I need 1 water, don't I? And then I balance hydrogens with the hydrogen ion. Okay, so we're starting out exactly the same way as we did with the acidic. Now here's where it differs, and you'll notice I have these, a new step, step 5. Now what we're going to do, because it's basic, is that we're going to add the exact number of OHs as we have H's to both sides. So to this side, I'm going to add 2 OHs. And to this side, I'm going to add 2 OHs. Okay? Well, what happens to this? This becomes 2 waters. All right? So really, what you're doing is this is always going to reduce down to that number of waters. So if I had 4 H's, when I add 4 OHs, it's going to be 4 waters. So you can cut to that right away if you want, or wait. So what we have now in the basic solution is we've done this exactly the same way. The only thing changing is adding those OHs, and now we obviously have a basic solution. All right, so now this is balanced as far as mass, and we have to look at charge. On this side, I've got 2 plus 1 is a minus 3, And over here I've got a -1, don't I? I'll clean this up a little bit. And this is what you have to be careful with basic, is that you just keep it cleaned up. Else it gets so sloppy you can make stupid errors. Not that you did it wrong, you just added wrong. All right, so I've got a 3- on this side, I got a 1-, so I need to add 2 electrons. Okay, now we're going to do the same thing with the other half reaction. We got permanganate going to manganese 4 oxide. All right, the manganese is balanced. I balance oxygens with water, 2H2O. All right, I balance hydrogen with the hydrogen ion, 4H. This is a basic solution, so now I have to put in that additional step of adding however many H's I have to add the same number of OH's on both sides. Okay. This instantly is converted to 4H2O's. Because we know the formation of water is a driving force of a reaction because of that huge K value, right? So you're not going to have that sitting there. They're going to come together and form that water. All right, now I'm going to clean this up again. It looks a little messy. Okay. Now I'm going to balance the charge. On this side, I've got a -5. On this side, I've got, oh my, that can't have happened. What did I do wrong? Because I can't have electrons on both sides. That's a no-no. 2 waters, 4 H's. Two electrons. Oh, okay. No. Oh, okay, yeah. I'm sorry. I was just looking. I've got, oh yeah, but I can't do that. See, even me, and this is why I need this pause button on this. I gotta figure this out real quick. Then there's a 4, then there's 4. And that's a -5. Can't have one reaction